is that I want to go over this example. So remember, we're using kinematic equations. There's still only one table that we care about, right? We only care about one table. Everything has to be derived from this here, right? That is our table right here. So we want to use this table to calculate everything. All we know about projectiles is we know this. We know that AX is equal to 0 and AY is equal to minus G. That's it. Okay, so let's read the question here. So it says here that you have an airplane with the speed of 80.6 meters per second and is diving at an angle of 30 degrees below the horizontal when the pilot releases a radar decoy. Sure, it's releasing a radar decoy. Now, the horizontal distance between the release point and the point where the decoy strikes the ground is 700 meters. A, how long is the decoy in the air? And B, how high was the release point? C, what is the final velocity of the decoy? So the first thing that we want to really think about here is that we know that this airplane is diving. So let's make sure that we're thinking about this with good physics here, right? We want to think good physics here. So what we want to do here is that I want to make sure that we're really clear. What do I mean by the initial velocity here? So it says that the airplane is moving at 80.6 meters per second and it's diving. So let's draw a plane. Okay, so here's my plane. So let's say that this plane is doing this. So as it's flying, what we're seeing here, right, it's a Blue Angel. We know that it has some exhaust that's coming out here. And what we want to do here, I'm going to say that this is my little decoy, right? We're going to say there's the decoy and it's carrying the decoy. So for right now, I'm going to assume that the acceleration is 0. So if the plane is moving at 80.6 meters per second, how fast is the decoy moving? Has to be 80.6 seconds too. So now what's going to happen here is that we're going to go into a process here, and look what it says here. It's trying to be very careful on how it says it here. It says that the pilot releases a decoy. Now, some people may think that because it's being released, it may be at rest when it's being released. But that can't be true. Because if the pilot is moving at 80.6 meters a second, so is the decoy. So now the airplane is now in a dive, right? We're thinking about this dive here. Well, that looks like the space shuttle here. And so as it's in a dive here, what you're seeing here, right? You're finding that the airplane is at some angle. What's the angle? Well, here's the horizontal. So wait, let's put the decoy in here. So what you're going to see here is that the decoy is now being released here. So when I'm thinking about this, here's what I'm thinking here. I'm thinking here's my axis right here. Like this. The decoy and the plane at this moment have an initial speed of what? 80.6 meters per second. And what we know here is that from here to here, there's an angle of 30 degrees. So that means I know everything about the initial velocity of the airplane. Okay? I know everything about the initial velocity. So now what I want to do here is that the first thing that I got to do is that I got to go in and I got to calculate the components of the velocity. So let's go do that. Okay. So I have a picture here, and what we're expecting is going to happen is that, you know what? I think I need to step back a little bit. I need to do this a little bit more. So I'm going to come back here, and I'm imagining that I have my ground like this. So what I suspect is going to happen here is that as this thing flies, what's it going to do? It's going to take some curved path. It doesn't go in a straight line. And what we're seeing here is that what we just took advantage of right now is we took advantage of what? The speed and the direction. So now it says that the horizontal distance between the release point and the point where the decoy strikes the ground is what? 700 meters. That means there's a horizontal distance that it goes from here to here, which is 700 meters. Okay. So let's go look at my physical picture here, because as of right now, we're not clean. This is sort of like, excuse me, this is my physical picture. What I want is I want my mathematical picture. Okay. So if I go look at my mathematical picture, that means I got to take that velocity and I got to break it into components. I now know that I have a velocity, right? I have a velocity that's going in the x direction. I know that I have a velocity going in the y direction. And when I do the superposition of these guys, I know that's my initial velocity right there. And I know that this angle right here is 30 degrees. So I need those two velocity components. So let's calculate that. That's the only difference between the mathematical and the physical picture, is that I need those components. So let's go do that. So I know V initial is, what is it? 80.6 meters. So then my X is then going to be cosine of 30. Now let's be, right? And then my Y here is going to be V initial Y, which will be V initial sine of 30. Then I look at the quadrant. What's the quadrant? The quadrant is in the fourth quadrant. That means this has to have, let me move this over a little bit. Damn it. Okay, my bad. So that means if it's in the fourth quadrant, I know that the X component is positive. I know that the Y component is negative. So then I plug in my numbers. So then this is going to be 80.6 cosine of 30. And when I compute that, I get a value of 69.8 meters per second. And when I compute this guy, I'm going to get negative 40.3 meters per second. So I now have my velocities, right? I have my two velocities. So then I'm just going to go set up my tables right now so that I have that piece. So then I'm going to set up my data tables. And what do I know? I know that for X, then I have AX. Now note AX is 0. If AX is 0, I know that the initial and final velocities must be exactly the same. So I'm going to take this velocity right here, and that's the one that has to go into here, which will be 69.8 meters per second. And then I'm just going to keep putting in my next value, which is right here. So note, I did that I modified my table just because I knew the acceleration was 0. And then I'm looking for y here. So I have ay is going to be minus g. And then I have vy, v initial y, and t. And what you're seeing here is that now I have this velocity in the y direction. So I got to go in and put this thing here. So there's going to be minus 40.3 meters per second. Note how I immediately put in those initial velocities. What did I say? About 30% of you are going to ignore the components. And what are you going to do? You're going to come in here and you're going to put in 80.6. And then I just get my pen and I start taking a bunch of points off. Don't do that. This is vector motion, not linear motion. So then we keep moving along here. So then if I look at the question is reading what here? It says, A, how long is the decoy in the air? How high was it released? And what is the final velocity of the decoy right before it hits the ground? Okay, so A, how long is the decoy in the air? So the first thing that I need to do here is that we're asking, what is the flight time of the decoy? Well, let's keep going to our picture here. What we do know here is that our distance is 700 meters. And I think that's all that we have right there. And so when you're looking at this relationship, what am I actually seeing here? Well, you're seeing a couple of things. Note that time is in multiple places. So if I want to solve for time, you could see that I have time right here, and I also have time right here. But note, I don't have distance here, and I don't have final velocity, but you could see that I know everything in the x direction, so I could use the x equations to do this. So right now, it's impossible, right? What this is telling me, it's impossible for the y equations to calculate time. So I got to use the x equations. So then that's what I'm going to do. And remember what we said here, if ax is equal to 0, then there's only one equation. So here I go. So I'm going to solve for time using the x equations. And what we already said here is that there's only one relationship for the time. There's only one relationship in the x to get the time here. So what am I going to do? I'm going to solve this thing here. So if I solve for time, you could see that this guy's going to be, and then I go right off my table. This is 700 meters divided by what? 69.8 meters per second. Do you see me using 80.6, the initial velocity, the initial speed? No, I'm using my x component. And so when I compute that, I get a value of 10.0 seconds. So that is the time. So I now know the flight time of the decoy. So the second part of the question, if I remember correctly, they're asking at what height is the decoy, I'm writing decay, decoy dropped from. Well, for starters here, let's go back to our table here. And one of the things that I see right away here is that that's a y thing. So what I want to do here is that I'm going to come in, I'm going to steal this table right here, and I'm going to bring it back down here. And what I'm seeing here is that I'm seeing this. We now know what that time is. We just solved for it. And because we just solved for it, I'm then going to come in by my hand here and I'm going to go, I now know that this guy is 10 seconds. That's new information. But note, we're trying to solve for the height. So if we're trying to solve for the height, I'm then going to modify my table and say, this is what I'm looking for now. I'm looking for that height here. So guess what? We don't have the final velocity. So right away, I'm going to go to the kinematics table. And when I go to the kinematics table here, which we have right up above here, what do I see here? Well, what I see here is that if I have this relationship right here, you can see that the one variable that I don't have is this final speed, which then means I must use this equation right here. So let's go write that down. So if I go write that down, it looks like this here. It says that that I have what? Ooh, I have to, I'm just looking for my numbers here. So then what I'm seeing here is that I'm getting delta y is then going to be v initial yt plus 1/2 ay t squared. So you could see I have my initial velocity, I have my acceleration, I have my time. So I'm just going to start to plug my stuff in here. So this will be minus 40.3 meters per second times my time, which is 10 seconds. And then I'm going to get plus 1/2. Then my acceleration due to gravity, which will be meters per second squared. And then my time is 10 seconds squared. And when you compute that, I'm going to get a value that reads what? Minus 897 meters. That's my y here. Now, one of the things that you should note here is that when I look at this number, there's two things to recognize here. The first thing that you should recognize is that I have a minus sign, right? I have a minus sign. What does that minus sign mean? All it's telling me here is that the decoy fell downwards. It's giving me my direction. Okay? So when I'm looking at this thing here, I now know what the height change of when the decoy was released. So the final part of this question says this. C. What is the final velocity of the decoy? And what I mean by this, when I say final, it just means just before hitting the ground. So you could imagine that it's atoms above this thing here. But we gotta be really careful here because a lot of people interpret this as speed. This has nothing to do with speed. It has to do with velocity. So when I say the word velocity, that means vector. And if I say the word vector, that means it has magnitude. What do I mean by magnitude? I want the velocity to be the velocity when it hits, right before it hits the ground, horizontally and vertically. And then the other piece, of course, is the direction. And of course, the direction is the inverse of the y over x. So that's what we need to do when we do this here. So what are we expecting here? Well, we know that if I look at this thing, if this is the ground, and we're thinking this in terms of an axis right here, I would expect the projectile to be what? Pointed somewards downwards like this. In other words, I expect that Vy should be negative while Vx should be positive. So I immediately expect then that the angle that I calculate should be less than 0 or less than 0 degrees. So I expect a negative angle. So if I don't get a negative angle, there's a problem. So what do I got to do? I got to go and calculate the x and y components now. So now we calculate the components. So the first one that we want to look at here is, of course, the x one. And then we'll go in and look at the y one. So what's special about this? Well, for starters here, we know that the x component of velocity does not change. Why does it not change? Because ax is equal to 0. But if ax is equal to 0, then v initial x must be the same as the final x value. But wait a minute, we already know that. We know that this value from our table up above, from what we had, that value was what? 69.8. So this is 69.8 meters per second for Vx. So I have half of my components that I need here. Now, here we go. Now we want to go in and we want to calculate the y component of the velocity. So when I'm thinking about the y component, what I'm looking at is that we've already set up the table up here. So if let me redraw the table here. What we said here is that we knew that we had a table that looked something like this. And we just calculated the distance, so it's 8,973 meters. And then we have Vy, which we don't know, V initial y, and T. So I know for a fact that we know that the initial speed, we calculated this already. And then from the problem, we said that the flight time was 10 seconds. So that leaves me only one spot to calculate what that velocity is. So this implies here that we can use any equation. So we can use any equation. And that has Vy. So what I'm going to do is I'm going to pick this easiest one from the kinematics table, and I would say it's going to be Vy, V initial y plus Ayt. That seems to be the most logical one. And so if I plug in my values, you could see here that this is going to be 40.3. And then I'm going to get minus 9.8 times 10. So if I calculate this thing, I'm going to get a number that reads minus 138 meter per second. And now I have my Vy. So now I got all of my components now. So let's go calculate the final velocity now. The final velocity is The magnitude should be the squares of the x's and y's. So if I do that, since we have our numbers, I'm just going to plug those guys in. Note that Vx is 69.8 plus negative 138 plus square root that whole thing. And if you compute that, I end up getting 155 meters per second for the speed. I now know what the speed is, but I need my velocity. And the way I get my velocity is I got to take the angle. I got to get the angle. So here I go. So now the big thing that I got to get, which people have a tendency to miss, as I've already said several times, don't forget about the angle. So the angle, of course, is theta is equal to tan inverse. And I'm going to get minus 138 divided by 698 meters per second. You know what? I wrote 600. No, it should be 69.8. And I think up here, I don't know if I said 69.8, but if I calculate that, the first thing that shows me here is that I got a negative sign. That's exactly what we wanted. So when I compute that, I'm going to get minus 63.2 degrees for the angle.